morning, or afternoon, or evening, my lovely viewers, and welcome back to another episode of Maths. It is currently 10:57 in the morning, and if you're watching this at the same time, you need to go onto Instagram, follow me there, and DM me your home address. So last video, we talked about coprimes. Coprimes were basically this idea that we have a pair of numbers and they had no common factors except for one. And we saw that had some interesting properties regarding their greatest common factor, as well as their lowest common multiple. And today we're going to be practicing those concepts, getting used to the idea of coprimes and doing some interesting problems. Number 6 here, if you want to look at that, is particularly challenging, I think, but it's a really interesting one, and I'm excited to do it with you. But yeah, we're going to get used to the idea of coprimes because afterwards we got some videos that are going to rely on coprimes, and so it's important for you to really get this concept down. So we are going to get into it. As usual, pause the video, try these out yourself first, and then we are going to slap on over and do them together. Alrighty, question numero uno. Are the following pairs of numbers coprime or not? So this is just kind of a direct test of the concept where we took two different numbers and we saw if they had basically a common factor other than one. And so to do that, we prime factorized the numbers. So again, you're very comfortable with prime factorization if you've been following my videos because we've done this dozens of times by now. So I'm going to let you try out these prime factorizations for yourself and see if you get the same thing as me. Alright, so these are the prime factorizations that I got. And we want to see if they're coprime or not. That means they have no prime factors that are common with each other. But we see that 18 and 58 both have 2 as a common factor, which means that they have a common factor of 2, not just 1, and that means that these numbers are not coprime. The definition of being coprime was that 1 was the only common factor they had, or that they had nothing in common with their prime factorizations. So these are not coprime. Next up, 33 and 85. So go ahead and find those prime factorizations. Now with 33 and 85, do they have any common prime factors? They don't, right? This has 3 and 11, those don't appear over here. This has 5 and 17, those don't appear over here. So they have no common prime factors, which means that they have no common factors except for 1. So these are coprime. Alrighty, next up, 24 and 125. Take your guesses. Do you think it's going to be coprime or not coprime? Well, let's find out. Let's prime factorize them. Alrighty, and once again, like the one before, they have no common prime factors, right? This has 2s and 3s, this has just 5s, so these have to be coprime. Alright, this last one here, some slightly girthier numbers, but that's alright. Alright, so 1000 has the long prime factorization of 2 times 2 times 2 times 5 times 5 times 5, and 175 has the prime factorization of 5 times 5 times 7. Well, these definitely have some stuff in common. They have both of these 5s as common prime factors, which means that these have 5 as a common factor. They also have 25 as a common factor, so these are definitely not going to be coprime. Alright, so pretty simple concept, and yeah, that's just the idea. If you want some more practice, well, here's your extra practice. Pick random pairs of numbers just like I did and see if they're coprime. Find their prime factorizations, compare them, and you'll know right away if they're coprime or not. Alright, let's move on to number 2. Alright, number 2 says, show that this pair of numbers is not coprime without finding their prime factorizations. Okay, so we have some really juicy numbers here, like absolutely badonkulous, girthy numbers. And we do not want to find their prime factorizations. Absolutely massive. It's going to take us a long time. We could, right? We're capable, but it's going to be a long time. And part of math is finding efficient ways to do things, not just banging our head against a wall over and over again and like hoping that it's going to work out, because that takes a long time and that can be frustrating. So this is asking us to show that they're not coprime, but not using their prime factorization. So implying that there's maybe a more efficient method to do this. So how can we do that? To show that two numbers aren't coprime means that they basically have a common factor other than 1, right? So if we can show that these two numbers are divisible by the same thing other than 1, then we know that that number is their factor, right? So can we start with 2? Well, this one isn't going to be divisible by 2 because it's an odd number, right? But how about 3? All right, let's try that. So do you remember the divisibility rule for 3? We talked about this several videos ago now, but it's a very useful one that I recommend you going back and reviewing if you do not remember. But it was that we add up all the digits of the number and see if it's a multiple of 3. So for this number, which is 3,363,201, we're going to add up the digits. So that's 3 plus 3 plus 6 plus 3 plus 2 plus 0 plus 1. So that gives us 3 plus 3 is 6, plus 6 is 12, plus 3 is 15, plus 2 is 17, plus 0 is still 17, plus 1 is 18. Is 18 a multiple of 3? Yes, it is. So therefore, 3,363,201 is divisible by 3. All right, so if we're lucky, this next one is also going to be divisible by 3. So it's 150,810, so we do 1 plus 5 plus 0 plus 8 plus 1 plus 0. So 1 plus 5 is 6, plus 0 is still 6, plus 8 is 14, plus 1 is 15, and then the 0 does nothing. So we get 15. Is 15 a multiple of 3? You bet your bottom dollar it is. So that means that the number 150,810 is also divisible by 3. So what does this mean for us? Well, both of these numbers, they're divisible by 3, which means that 3 is a factor of both of these numbers, which means that they have a common factor that is not just 1, it's also a common factor of 3. So therefore, these numbers are not coprime. All right, and for extra practice, so just like with the previous question, I said like take pairs of numbers and see if they're coprime or not. But now you can maybe start to do it a little more efficiently where you don't just write out their prime factorizations, but maybe kind of from the get-go you can see, hey, these numbers are divisible by the same thing, and that thing is not just 1, it's like a common factor that's bigger than 1, so they can't be coprime. And so this is kind of a slightly more efficient method that you can start putting into your testing techniques in order to do the problems more efficiently and more quickly. All right, so that is number 2. Let's move on over to number 3. Alrighty, we got some true or false questions here. So number 1, the greatest common factor of two coprimes is their product. Now, if you remember from the video, I said that, okay, yeah, we can use the product of them to find, was it the greatest common factor or was it the lowest common multiple? It was the lowest common multiple, right? Because we saw that, okay, to find the lowest common multiple of numbers, you have to multiply their prime factorizations together, where you just, if there's a repeated element in their prime factorizations, then you just don't include that multiple times. However, with coprimes, they have no repeated element in their prime factorizations because they have nothing in common, so you had to just take the product of them. But again, that was for the lowest common multiple, not the greatest common factor. The greatest common factor of two coprimes was always 1, right? Because coprimes, by definition, have only 1 as a common factor, which means their greatest common factor has to be 1. So this one is false because it was mixing up greatest common factor with lowest common multiple. All right, let's do number 2 here. 1 is coprime with every number. Okay, so this is kind of an interesting one. So if we take 1 and some other number, are they going to be coprime? So 1 and another number. Well, to be coprime means that their common factor, their only common factor is 1. But is 1 going to have a factor other than itself? No, right? 1's only factor is 1. And every number has 1 as a factor. So that means that the greatest common factor of 1 and another number is always 1, which means their only common factor is 1, which means that, yeah, 1 is coprime with every number. So that's kind of like a unique property of 1, is that it's coprime with every single number. So it is true. Alrighty, number 3. Two different primes are always coprime with each other. Alright, so again, to be coprime, they have nothing in common, but these are two prime numbers. Alright, so these prime numbers, their prime factorizations are just themselves, right? Like 7, for example. 7's prime factorization is, well, simply just 7. 11's prime factorization is simply just 11, right? So because of that, if these are different than each other, then their prime factorizations automatically are going to be different than each other, right? There's nothing that's ever going to be in common with two different prime numbers, which means that their greatest common factor, their only common factor, is going to be 1. So two primes are always going to be co-prime with each other. So that's a true statement. And let's look at the last one of this true and false set. Primes are co-prime with every number besides themselves. So, I mean, that kind of feels like it should be true, right? Because primes, they are kind of these indivisible atomic things, so they should be co-prime with everything else. And that's almost always true, except for if we're taking a prime number and we're comparing it with a multiple of it. For example, 7, yeah, it's co-prime with 1, 2, 3, 4, 5, 6, 9, 10, 11, right? All those numbers. But what about with 14? It's not going to be co-prime with 14 because 14 has 7 as one of its factors, right? So since 7 and 14 both have 7 as a factor, their greatest common factor is going to be 7. It's going to be a common factor between them, and it's not just 1, which means that 7 is co-prime with any of its multiples. It's going to be co-prime with 14, 28, 35, and so on and so forth. So primes are almost co-prime with every other number. It's just that they're not co-prime with any of their multiples. So this statement has to be false then. All right, so that was number 3. Hope you found that interesting. And let's groove on over to numero 4. All right, so this one says find 4 different numbers that are co-prime to 12. So again, to be co-prime just means they have nothing in common with 12's prime factorization. So the first thing we should do is just simply find what 12's prime factorization is going to be, which is 2 times 2 times 3. And now that we know that, we just need to find 4 numbers that don't have 2's or 3's in their prime factorization. So we could do the number 5, for example. Since 5 has no 2's or 3's in its prime factorization, we could do the number 25, right? 25, which is just 5 times 5, no 2's or 3's in it. We could do the number, maybe let's do a bigger number. So let's do like 77, because 77, that's 7 times 11. So that has no 2's or 3's in its prime factorization. 115. 115 will be co-prime with 12, since 23 times 5 gives us 115. So basically, all we do is just find numbers that have prime factorizations that don't overlap with 12's, right? And so you can, if you wanted more practice, just find more numbers that are co-prime to 12, or more numbers that are co-prime to anything, right? The world's your oyster with these. So let's go on to number 5. Show that 2 even numbers are never co-prime. All right, so this is an interesting statement. 2 even numbers are never co-prime. If we look back at the first question, we were looking at 18 and 58, and we saw those weren't co-prime. And they weren't co-prime, well, because they both had a 2, and these are both even numbers. So maybe we can use that to show that 2 even numbers in general aren't going to be co-prime. So 2 even numbers, what is the property that all even numbers have? All even numbers have 2 as a factor, right? We showed that in a previous video where we said that every even number is divisible by 2. So I'll write that down. Since every even number is divisible by 2, that means it has 2 as a factor of it. So that means when I compare 2 even numbers, that means they both have 2 as a factor. So that means they have 2 as a common factor. And 2 is not 1, right? 2 is bigger than 1, so 1 isn't their only common factor, which means that they can't be co-prime. So let's write that down. All right, so every even number is divisible by 2, so they have 2 as a factor. Thus, any 2 even numbers have 2 as a common factor, and thus they can't be co-prime. All right, so that was kind of an interesting one, and we were making use of the divisibility laws that we learned earlier in the series. So let's go on to the final question, the hardest question, but the most interesting one in my opinion. That's right, number 6. Show that any 2 successive numbers are always co-prime. So what do I mean by successive numbers? I just mean numbers that come after each other. So we got 2 and 3, 16 and 17. If we add 13, the next successive number would be 14, right? So it's just the number that comes after it, right? And I want to show that if you give me any pair of 2 successive numbers, those are always going to be co-prime. So we can start with some examples, right? Like 1 and 2, that's the first pair of successive numbers that are positive. And we have, okay, 1 and 2. So these are co-prime. We know that because we showed in an earlier one that 1 is co-prime with anything. All right, the next pair is going to be 2 and 3. Well, do 2 and 3 have anything in common? No, they don't, right? They're both prime numbers, and so that means they are co-prime. 3 and 4. 3 and 4, once again, have nothing in common, right? 4's prime factorization is 2 and 2. That doesn't include anything in 3's prime factorization, which is just 3. So this pair is also coprime. And we can keep going like this, right? But we're going to see that every single pair of successive numbers should be coprime. So how do we actually go about showing this? How can I show that this is true for every single pair? Because obviously I can't just check every single pair. There's an infinite number of them. So how do I show that any two successive numbers are always coprime? So what does it mean for two numbers to have a common factor? Well, it means that basically both of those numbers are multiples of the same thing. So two numbers have a common factor if they are both multiples of it. So for example, 8 and 12 have a common factor of 4, since they're both multiples of it. Also, my pen's starting to die here, so I'm going to switch over to another color. So two numbers have a common factor if they're both multiples of it, right? 8 and 12 have the common factor of 4, since, well, 8 is a multiple of 4 and 12 is a multiple of 4, right? So that means that if we consider two successive numbers, they can't be multiples of anything bigger than 1. Right? If they were multiples of 2, then they would be 2 apart from each other. If they were multiples of 3, they would be 3 apart from each other, right? Multiples, we're just counting by that number. Multiples of 3 are counting by 3s. Multiples of 4s are counting by 4s. But if these numbers are beside each other, they can't be separated by anything more than 1. So if we consider two successive numbers, they can't be multiples of anything bigger than 1. Since they're only 1 apart. 8 and 12 were both multiples of 4. They're 4 apart from each other. So first of all, we knew that 8 was a multiple of 4. We added 4, we got 12, so it's also a multiple of 4, right? So they had a common factor of 4. But here, two successive numbers, they aren't separated by anything more than 1, right? They're right beside each other. So they can't both be multiples of 2. Maybe one number's a multiple of 2, but then to get to the next one, we have to add 2, which is going to skip over this successive number. So we know that they aren't multiples of anything bigger than 1, which means that they only have a common factor that's 1. So their only common factor is 1. But what does that mean? It means that they're coprime, right? Their only common factor is 1, they have to be coprime. And so this is a pretty useful statement, is if you give me two numbers and they're immediately beside each other, you don't have to check anything, they're automatically coprime. And so just like checking with the divisibility laws, this is an even more efficient way of seeing if two numbers are coprime. It's a really specific case, but if you ever see it, you don't have to check any further. You just know that, hey, they're successive, they're one next to each other, they gotta be coprime. I think that was a really cool question. Let me know what your thoughts were on it. Well, that's gonna do it for today's episode. I have 2 coprime application videos planned, which are both really cool and really interesting. And even after that, we're still going to be using these bad boys. They're really useful, and you can expect them to come up all the time. That's going to do it for me today. Have a good one, stay groovy, follow me on Instagram, and I'll see you in that next video.